Imagine you're trying to make a complex decision, say, whether a customer should buy flight delay insurance. Now imagine you could gather a room full of experts, each with their own perspective and experience. Instead of relying on just one opinion, you listen to all of them and go with what the majority recommends. That's the basic idea behind the decision forest algorithm, more commonly known as random forest. Unlike a single decision tree, which follows one clear path of logic, a decision forest builds many trees, each trained on slightly different versions of the data. It doesn't just trust one, it takes a vote across all of them and decides based on the majority. This collective decision-making process makes the model far more robust and accurate. Here's how it works. The algorithm starts by taking random samples from the original dataset. Some data points may be repeated, and some might be left out. This is known as bootstrap sampling. Then, for each of these data subsets, it grows a separate decision tree. But that's not all. To make sure the trees are diverse and don't all learn the same patterns, each tree is also trained using a random subset of features. In other words, each tree looks at different parts of the problem. This randomness ensures that the trees each bring a unique viewpoint to the table. When it's time to make a prediction, each tree casts a vote. For classification problems, like deciding yes or no for buying insurance, the forest goes with the majority vote. For regression problems, where the goal is to predict a number, it averages the outputs from all trees. This approach has some powerful advantages. First, by combining many trees, it reduces overfitting, a common problem where a model learns the training data too closely and fails to generalize to new situations. Random forests are also very flexible. They work well with different types of data, numbers, categories, they're resilient to missing values, and they can even tell you which features are most important for making predictions. But like any method, it's not without its trade-offs. Since it uses many trees, a decision forest can be slower to make predictions and use more memory. And because the final decision comes from a consensus of trees, it's harder to explain exactly why a certain decision was made. This can be a challenge in highly regulated industries where transparency is required. Let's return to our insurance example. Suppose the model is trained with data on airlines, seasons, weather forecasts, destination airports, and historical delay rates. The decision forest creates dozens, or even hundreds, of decision trees, each using different slices of this information. When a new customer comes along, the forest considers their data, runs it through all the trees, and tallies the results. If most of the trees suggest that buying insurance is a good idea, that becomes the prediction. In essence, the decision forest is like assembling a wise panel of advisors. No single voice dominates. Instead, each one contributes to a more balanced, reliable conclusion. It's one of the reasons why this algorithm is so widely used in real-world applications, from fraud detection and medical diagnosis to customer behavior predictions and beyond.